The next talk will be of Lorenz Eberhardt, Rademacher, evolution of one-loop string amplitude. Please, Lorenz.
Thank you very much. Thanks very much to the organizer for organizing this wonderful conference. It's really nice that it's actually a conference about string theory and you don't have to shy back to say technical details and so on, so I really enjoy it. This talk is not about integrability in the traditional sense, but it's about computing integrals in string theory. So in that sense, we're still doing integrability. And it's based on a series of papers that I started writing like 3-4 years ago with Sebastian Misera. And in the meantime, other people joined for part of the fun. And yeah, so it's really going back to the roots of string theory and trying to compute amplitudes. Okay, so first, if you've never been in contact with string amplitudes at higher genus, and maybe you computed one-loop amplitudes of QFT in your QFT course, you might have the impression that in string theory it's similar, but it's much more complicated. And I think surprisingly little is known about string amplitudes at higher loops. So let's start and look at our favorite formula for the scattering amplitude of gravitons in string theory at tree level. It takes this very nice form. So there's some tensor in front that takes care of all the polarization dependence of the 2-to-2 graviton scattering that is completely known, and it's the same at every loop order. So in some sense, it's boring. And the interesting part is this, the dependence of the amplitude of the three Mandelstam variables st and u, and it takes this very nice form. And let me just point out some of the amazing properties. It's manifestly crossing symmetric, and it's just one term, so it's not a sum of different diagrams as you have in field theory. This is the old idea of dual resonance. It is Regge bounded in the Regge limit. It's UV soft, as we already heard previously in the conference. So if you go to very high energies at fixed angle, the amplitude decays exponentially fast. And of course, it's also consistent with unitarity. So it's actually very hard to cook up functions that do all of these things. So even if you don't know about string theory, just try to write down a function that does all of these things. And maybe you have the impression that if you go to a higher loop, there's an equally nice expression, maybe with slightly more elaborate special function, but somehow this is not really close to the truth. So today I will try to explain a general idea that we have about computing this one-loop string amplitude. And in some sense, it's a technique to compute certain integrals over modular parameters. So if you encounter an integral over a modular parameter, then you can also apply this technique, even though it has nothing to do maybe with string amplitudes. All right, so first of all, to convince you that there will be some result. So what we mostly care about is actually, getting the plot. Like if an experimentalist would ask us, like, what's the signature we should actually look for if we could build your great collider, then unfortunately the truth is that beyond tree level, we couldn't actually tell them what kind of amplitude they should look for. And so this is the plot of the one loop piece of the amplitude. So I've not plotted the tree level. This is just a one loop correction. And I plotted as a function of the energy. Here I put alpha prime to be 4, so in the previous units, just so that all the poles of the amplitude sit at integers. And you see, again, this is plotted at fixed angle, and the amplitude goes exponentially down, also at one loop. We'll talk more about this, but it has a kind of non-trivial structure to it, and the blue curve is the imaginary part, and the yellow curve is the real part. The imaginary part will be much easier to compute because it's determined by the optical theorem from tree level, whereas for the real part, we really have to work. And you see it's not perfect what we do because there's some kind of numerical error. And also, I want to mention that there has been a lot of work in the literature by these people, plus probably other people that I haven't mentioned, in trying to understand the low energy expansion of the amplitude. So if you take the amplitude, you go to low energies, meaning down here, before the first massive string state appears, then you're basically talking about QFT with higher derivative corrections. And you can compute the amplitude systematically in this alpha prime expansion. So it's known to 7 orders or something like this. So we just took the answer that you can find in literature and you plot it, and you see that kind of reasonably fits. And for reasons I'll explain later on, this is actually the region where we have most trouble in applying our method. All right, so we'll come back to this later, but this is just a short preview. So what the talk will be about is to first I will explain what's the actual integrals we need to compute, because there's some fine print in trying to define string amplitudes. Then I'll explain how this evaluation works, this Rademacher method, and then we'll talk a little bit about physics in the end. So let's get started. And so if you read any textbook on string theory, they usually tell you that a string amplitude is computed as follows, schematically. So you want to understand some endpoint amplitude at genus G. What you need to do is you need to compute some CFT correlation function of the worldsheet. There's just flat space, to be clear, and then integrate over the moduli space. There might be some fine print. If you do the superstring, then you need to worry about picture numbers and so on, but let's not worry about that too much. But the thing that I want to point out is that this integral is pretty formal, because typically it's divergent. And the integral diverges from the boundaries divisors of moduli space. So these are regions in moduli space that describe surfaces where some part of the surface pinches and some part becomes very long. And all these singularities, because there's a part of the surface that becomes very long, they're all IR singularities in space-time. So there's nothing to say that string theory is somehow wrong. There are no UV divergences or something, but there are many IR divergences, and they lead to physical features in the amplitudes, like poles and branch cuts and so on. Okay, so this is something that we do actually expect, because, for example, this thing is fully real. So if we integrate it, and the integral would make sense that our amplitude wouldn't have an imaginary part, which, of course, it should have. Okay. So, and there are several solutions to this, but I think a particularly nice one was discussed by Witten about 10 years ago, is that actually what you need to compute is this integral, but what you forgot in writing this prescription is you forgot that the worldsheet is actually Lorentzian. So everyone loves Euclidean 2D CFT. It's very nice and so on, but at the end of the day, we need to care about the causal structure of spacetime. And so there's a Lorentzian direction on the worldsheet. And what that means is that we should not integrate over the moduli space of Euclidean Riemann surfaces, but we should integrate over some kind of moduli space of Lorentzian Riemann surfaces. And what that means is, so you take the moduli space, MGN, you complexify it, which means now you don't care about whether it's Euclidean or Lorentzian. It could be some complex metric on the worldsheet. And then you need to pick a particular contour in this complexified version of the moduli space that you need to integrate over. So the naive contour is that you pick the contour of the Euclidean worldsheets, but that leads to ill-defined integrals. And in fact, what Witten explained is that whenever you go close to, so this contour, this Euclidean contour is fine as long as you stay away from the boundaries of moduli space. But if you approach one of the boundaries, then you get a part of the worldsheet that becomes very long, and you can think of it as being basically a word line. If you don't look very closely, it looks like a word line in QFT. And then we know what to do, because this moduli space, all these moduli, they become the Schwinger parameters in QFT. And what we forgot to do is to implement the I epsilon prescription. Like Schwinger parameters are really Lorentzian, and they have some I epsilon prescription. And what that means is that this contour will get modified and goes off in some complex direction. So this is sometimes called the stringy I epsilon prescription, but it's a version of the Feynman I epsilon prescription in string theory. And in particular, that is responsible to give you all the imaginary parts and so on the amplitude. Okay, so I'll not tell you exactly how that works, but just let me tell you how it works for the one-loop amplitude. So then, well, you go and you, sorry, I should have mentioned Green and Schwarz here. So this is the classic result of Green and Schwarz for the one-loop amplitude in type 2 string theory at one loop. So they tell you, like, after you go all through all the picture changing, summing over spin structures and so forth, you get some very nice integral that you should compute at one loop that they tell you is the answer. And they also already stripped out, there's also this T8 tilde, this polarization dependence that I'll just strip out because it's some overall prefactor. I only care about the actual kinematical dependence. Similarly, there's some G string to the fourth in front that I'll also forget. Okay, so they tell you you need to compute this integral. And that looks like a pretty easy task. So it's some 8-dimensional integral, so you would think, okay, just put it on computer. But in particular, we already know that the answer has this very exponentially decaying feature. But if you look at the integrand, it actually seems to be exponentially growing if you make the energy bigger and bigger. So there's some huge amount of cancellation in it. And that makes it very tricky to evaluate, say, numerically. So, and what is this I epsilon prescription doing? Let me mostly focus on the part of the integral that is over tau. There's also the part of the integral that is over z, but it's sort of less harmful, let's say. So in particular, in tau, we need to integrate over this fundamental domain. And so there's the CASP in the fundamental domain where we get all these divergences from. And what we need to do is sort of what is schematically drawn here. So you go to the CASP, but before you arrive at the CASP, at some point you decide, well, now your torus is very long and you're basically doing QFT, and you need to complexify and turn off in the complex plane. What that means is you formally you take the real part of tau and the imaginary part of tau, you write the integrand as a holomorphic function x and y, in the real part and in the imaginary part, and now you complexify x and y. And you let the contour, so in x it just goes from -1/2 to 1/2, but in y it turns into the complex plane. Okay, so slightly funny because the moduli space itself is complex. So you first have to forget that the moduli space that you integrated over is complex, and then you complexify it again, and then you can go off in the complex plane. That sounds confusing. Think about the open string. In the open string, you have just a one-dimensional integral, and that integral is over the imaginary part of tau, and then you can go off in the complex plane. It's the same thing. Okay, so this is, and once you integrate over this contour, everything is convergent, because all of this stuff will be oscillatory in this direction, and there's this 1 over im tau to the 5 that makes everything converge. And you have a choice whether you come out of the board or you go in, and that's the sign of the I epsilon prescription. Okay, very good. So now we know what, in principle, the integral is that we should compute. How do we compute it? So this is still not very useful. So this is what I basically just said, that if you try to put it on a computer, well, it's convergent, but there's so much cancellation that it's the same problem in quantum mechanics all over again. So we don't really know how to usefully put this on a computer. So instead, we'll apply a series of contour deformations, because now we have some high-dimensional contour, and we have a holomorphic integrand. It's holomorphic in this complexified sense. So we can freely move around our contours and have fun. So, and for the real part, this will be fairly difficult, but for the imaginary part, it's not so hard to understand what to do. Because for the imaginary part of the amplitude, we know there's an optical theorem. So that should be simpler. And indeed, it is. So if you want to compute only the imaginary part, what you need to do is you take the difference of the two I epsilon prescriptions. So the one where the contour goes out of the board and the one where it goes into the board. And in this difference, the real part will cancel out, and the imaginary part will add up. So if you want to compute the imaginary part, it is just computed by the contour that's schematically drawn here that goes sort of in the board. And why is this contour much simpler to evaluate than this contour? Because everything's holomorphic, so we're freely allowed to move around this contour. It's a two-dimensional contour, so maybe hard to think about. But basically what you can do is you can push it up as much as you want. You can move it as close as you want to the CASP. And what that means is that you only need to know about the local behavior of the integrand near the CASP to evaluate this integral. That's why it's easy. So let me show you at the toy example how that works. And maybe you got taught in your string theory course that you shouldn't compute one-loop determinants of the bosonic string, but it's a perfectly fine integral that you can compute, but it will turn out to have an imaginary part. But so I will explain some of the techniques at this toy example, just because it's simpler. So say you want to compute this bosonic string one-loop partition function, and let's first compute the imaginary part. So then we have to compute the integral over this contour, this imaginary part contour, that's the one that goes into the board. Well, so now, because we can push it up to we can make the imaginary part of tau as big as we want, we can plug in the Q expansion of this 1 over eta to the 24. And there is the term that corresponds to the tachyon, and then there are subleading terms. And all the massless terms, they will die, because if I push this to higher and higher values of im tau, well, this 1 over im tau to the 14 will suppress me more and more. And then there are the even more subleading terms, and they will die exponentially. So they die even more. So that means it's an exact thing to just omit all these subleading terms. So we're only sensitive to terms in this integral that blow up near the CASP. So this is precisely the term that you got taught that is bad in the one-loop amplitude, because if you integrate over it, it makes it not convergent. But once you have the right contour, then well, this is a term that has an imaginary part, but fine. And then, okay, it's kind of elementary, then you integrate with the real part. This doesn't depend on the real part, and then if you call the imaginary part y, then some kind of elementary integral, you get some power of pi. But this is just to say that it's easy to do. Okay, so if you do this for the full amplitude, you need some extra tricks and so on, but the final result is as follows. So you want to compute the imaginary part of the amplitude, and it takes, by doing the same kind of trick and pushing it up to infinity, you pick up some number of terms. Those number of terms are labeled by the masses of sort of what we call m down and m up. So this is the amplitude, and what you will reproduce is unitarity cuts in QFT, and you can have some massive string state down here labeled by an integer md, and the mass will be square root of md, and there's some integer up here, and you need to sum over all possibilities. Then you need to integrate over the on-shell phase space. There's some gram determinant that comes from this integral. And then there's some sum over polarizations. And in principle, if you would do this in field theory, it will be incredibly complicated to work out the sum over polarizations as soon as you include massive string states. But if you derive it from the one-loop amplitude, there's a very nice generating function for the sum over polarization. So this is something that we can compute pretty high up. In particular, it's a square. So I wrote square because it's the same sum over polarizations that appears in the open string. So this part double copies from the open string. And then you get a massive version of the Veneziano amplitude for the, or Virasoro-Shapiro, sorry, for the left, and a massive version of the Virasoro-Shapiro amplitude for the right part. So this may look complicated, but everything in here is easy. And in particular, all this integral, so now it's just a two-dimensional integral, and it's absolutely convergent, and it's very easy to put in a computer. So this tells you what this blue curve is. And you see the blue curve is very much smoother than the yellow curve, and you can already see that. And just to point out, like even if you go to only s equal to 8, so we can in principle go higher, but already here, like if you would do it in field theory, you would need to care about roughly 10 to the 22 states that are being exchanged, just because the number of massive states in string theory grows pretty rapidly. Okay, but now let's come to this Rademacher story and try to evaluate the real part. And the idea is the same. So we saw that the imaginary part is kind of easy to evaluate because it's only sensitive to the behavior of the integrand near cusp of the moduli space. But the moduli space you can see has more cusps, because so once you talk about this complexified moduli space, you can, for example, take tau to infinity, but you can take tau bar to some rational number. That's a cusp in the complexification of moduli space. And it turns out that you can evaluate the real part by knowing the behavior of the integrand near all these complexified cusps. So to explain this to you, it's a bit hard to draw 8-dimensional contours. So I will draw a 1-dimensional contour, and this is actually the one that appears for the open string. But I thought the closed string is more exciting, and it's more recent that we worked on it, so I wanted to show the pictures of the closed string. But for the open string, you would need also to compute some integral over some modular parameter, but there's a 1-dimensional integral. Whereas for the closed string, it will be a 2-dimensional integral. And what you do is some kind of series of contour deformations that Rademacher came up like 80 years ago in the context of analytic number theory. And basically what his insight was is that when you try to compute some integral over a modular parameter, so this is a 1-dimensional integral now, you can deform it into this integral that goes around these circles. Okay, this sounds very mysterious. So these circles are circles that are that touch the real axis at all the rational numbers, and they're all modular transformations of each other. So if you apply some SL to Z transformation to one circle, it gets mapped to other circles and so on. And they all touch each other in this nice way, and they don't overlap. They're called Ford circles. And they're very nice, but okay. But for some reason, you can deform the contour like this, and then you keep going. So this is, let's say, in the 5th step of this deformation, you go around all the circles, all the Ford circles whose denominator is at most 5. So you go, so here's a big circle, it's the 0, 1 circle, so you follow that one until you hit the 1/5 circle, you go around the 1/5 circle, and until you hit the 1/4 circle, you go around that, so 1/3, 2/5, and then 1/2. If you do the next step, then you also need to go have this small dent in here in the contour and so on, okay? So and then you keep doing this procedure, and you cross your fingers, and you hope that it converges, and you take everything to infinity. And in the limit, your contour goes around every one of these circles exactly once. So you can already see here, it almost goes around the 1/2 circle almost completely. If you go further and further and further, it will go more and more around all these circles. And then the point is that once you go have the contour as a sum of these circles, well, all these circles I told you are modular transforms of each other. So in particular, you can, if you want, you can map them to a horizontal contour, and then you can push that back up to infinity, or you can also say, well, you can shrink these circles, right? It almost seems like this contour should give 0 because it's contractible. But because the integrand has an essential singularity here, it's doesn't give 0. But you can make the circle as small as you want, and you're only sensitive to the local behavior of the integrand near these rational numbers. Okay, and then those are kind of similar to evaluate as the imaginary part. So now we want to apply this for the closed string, and I'll explain again at the example of this toy example how that works. So what we want to compute now is this integral, this one loop partition function over this funny contour. And the goal is to evaluate it in terms of its behavior near all these complexified cusps. And by that, so now you have tau and tau tilde. Tau tilde I call minus tau bar, so that's also in the upper half plane. So both, they live in the complexified version of modular space, which is 2 copies of the upper half plane, modded out by 1 copy of PZ2Z. And so what we need for this is a 2-dimensional version of the Rademacher expansion. And because it's a 2-dimensional contour. So this was not available in the math literature, but fortunately Tom Hartman and student Jiman Chandra, they told us a trick. This is basically some kind of version of the Lorentzian inversion formula in 2D CFTs that allows you to holomorphically split the tau and tau bar variable, and then you can apply Rademacher expansions on those separately. And so ultimately, after some steps of contour deformation, you come up with this formula. So it's a quite general formula that works whenever you want to compute an integral of a non-holomorphic function over the fundamental domain. So I'll just state it for the real part, because for the imaginary part, again, it's easy. And the real part of this answer is evaluated as an infinite sum. And this infinite sum is just a complicated way of saying all the fractions between 0 and 1. So the c is the denominator of the fraction, and a is the numerator. It goes from 0 to c minus 1, and it needs to be co-prime. And then you get contributions from all these circles. So because it's invariant in the modular transformation, you can always map this circle to be the horizontal one, which is like the 4th circle around infinity, if you want. And the other one, all these circles at all these rational numbers that we just had. And then there's some extra factor here. So this, in particular, there's some number here. This is the Dedekind sum, is some number theoretic thing that you don't need to care about. It's just basically measuring some kind of multiplicity of these of this contour inside the initial contour. And there's also some simple extra factor here. And unfortunately, I won't have time to tell you the full proof, but I encourage you. It's kind of fun to go to look at the paper. Yeah, so it's some combination of Lorentzian inversion formula and Rademacher expansion that ultimately gives you that. So once you have this, you can, for example, apply it to the toy example. And what you find if you just plug it into this formula, well, the point is that the integrals on the right-hand side are easy to do because you can shrink them. So they're only sensitive to the local behavior. And you can just fully evaluate it. So what appears are some Bessel function here, and there are some phases. So A star is the modular inverse of A mod C. And this is a very rapidly convergent sum. And then, of course, you have the imaginary part that we computed before. And I should really mention that this works in principle for any modular invariant function, provided it satisfies a certain boundedness condition. So modular invariant function that you need to analytically continue in terms of tau and tau bar, and it needs to satisfy some boundedness condition which is needed for this to converge. So basically, yeah. So, but the kind of integrals that we have here do satisfy this. All right. So and then we apply this for the full string amplitude. Then it becomes a little bit more complicated, but you still get the sum over fractions. You get also additional sums because there's also the z integral, so there's some sum over some kind of winding. and then you get these building blocks, and each of these building blocks is kind of manageable. And that is our formula. So it looks kind of complicated in the end, but I promise it's better than the initial integral that you write down in the beginning. And in particular, it's a convergent representation of the amplitude. And it's kind of practical to put on a computer for roughly this range of S. So it depends a little bit if you want to compute the full amplitude, and roughly we can go to S equal to 10. If you want to compute some special things like decay with mass shift and so on, we can go higher. For very small s, it turns out that the convergence breaks down. And the reason for this is that the amplitude has a massless branch cut that is not manifest in our formula, and it manifests itself by the sum over c over all the fractions breaking down. That's why in the initial plot, the region for very low energy is actually much worse. But there we can do direct numerical integration. There it's pretty good, or alpha prime expansion. Okay. So now let's talk about physics. And let's start by computing the amplitude in the forward limit. So this is a similar plot as the one I showed you in the beginning, but now we put t to 0 and just plot in terms of s. And we also multiply by the sine pi s squared. This is just because the amplitude has double poles at all the integers, so we multiply by the sine pi s squared to get nice plots. So this amplitude asymptotically goes like 1 over s, roughly. So that's why we multiply by s. This is something that we know from Regge physics. Regge physics, this is the Regge limit for very large s. And Regge physics tells us that, first of all, the amplitude is mostly imaginary for large s. And it is also goes like 1 over s. And this is asymptotic. You see it's actually very bad. The reason for this is that the error is of order 1 over log s. So you need to go to extremely high s to actually see that, which we can do for the imaginary part, but not really for the real part. But everything that we find here is consistent with the expectation from Regge physics. In particular, these Regge asymptotics were worked out a very long time ago by Amati, Cefaloni, Veneziano, and also Bosunburg. Maybe this is very similar in some sense to QFT, because all this Regge boundedness is also true in QFT. But what's very different is these fixed angle scatterings. So this is, again, the same plot as in the beginning. And in particular, for very large energies, there's this expectation from Gross-Mende that you get this exponential decay. But to my knowledge, this has never been checked or made precise and with all the numerical factors. And as I want to convince you, it's also not quite true what they write in the paper. I mean, it's morally true, so you get this exponential decay, but you see there's a lot of structure on top of it. So what they correctly predict is sort of the envelope of the answer, but not the actual answer. And importantly, the exponential decay, if you were to draw the tree-level answer, the exponential decay here is actually half as fast as for the tree-level. So the higher in loop you go, the less the exponential decay is. And the reason is because, so this comes because you do the moduli space integral by a saddle point approximation, and the saddle at one loop is a double cover. So the four-punctured torus is a double cover of a four-punctured sphere, which is the saddle at tree level. And the reason that is half comes because it's a double cover. Just to plot this in a different way, so for example, we can compute this decay width to very high order and divide them by the prediction of Gross-Mende. And you see it's order 1, this plot, but it has a lot of feature on top, again, that's not captured. We understand why that is, because there are many other saddles that were not taken into account in Gross-Mende, which are not on the real part of moduli space, but they sit somewhere off in the complexification of moduli space, and they do also contribute to this answer. And so if you want to so qualitatively Gross-Mende is right, but quantitatively you need to include various other saddles to get actually matching numbers. So that's we're working on currently, so stay tuned for that. Okay, so that brings me to the end. So let me summarize what was going on. So the main message I want to convey is that somehow people haven't played a lot with contour deformations in string perturbation theory, and they're very powerful, these techniques. And they allow you sometimes to get exact evaluation of string amplitudes. In particular, it's numerically very useful because it kind of avoids this exponentially cancellation that you have in the explicit integrals that like Green and Schwartz wrote 40 years ago. And to evaluate these integrals by these contour deformation methods, you only need the behavior of the integrand near the Lorentzian cusps, which again I drew here in the background. If you stare precisely, so that's the picture you have in mind, and you can shrink all these circles, and all the integrals over all these circles are only sensitive to what happens very close to the real axis. And these formulas make a lot of analytic structure manifest, not all. For example, the massless branch cut is not manifest, but a lot of massive analytic structure is made manifest. And it in particular allows us to make contact and check this high energy Gross-Mendel limit. So thanks a lot for your attention.
Questions?
So is there some way of thinking about the structure that you find on top of Gross-Mendel as like quantum corrections away from the saddle point? Or?
No, it's generally different saddle points. So there's more than one saddle point. So there's the Gross-Mendel saddle is this double cover of the sphere. But then there is a sort of complex, it's hard to picture because it lives in this complexification of modular space. So it's not a Riemann surface, but it's a complexification of that. So roughly speaking, the left moduli can be different from the right moduli in these other saddle points. Yeah, I don't know how to. Something like this, but much milder, already happens at tree level. That if you take Gross-Mendel at tree level, you would not see, like, for example, the poles at all the integers. They come in some sense because you go on the different sheets. So the integrand, let's say you do the Veneziano amplitude, is like z to the minus s, 1 minus z to the minus t. And it has branch cuts once you are willing to complexify that. If you go around these branch cuts, you pick up various phases. And when you resum the phases, you can get correctly the poles. Yeah, and something similar happens, but it's more drastic. It's not just phases. No, the multiplicities are not clear. They follow ultimately from like all this Rademacher discussion. But it's so if you're a completely honest person, you would need to first determine what are all the left shift symbols, steepest descent contours, and so on. And that's an absolute mess. So in particular, there are infinite number of saddle points and so on. So I don't know how to do that. Yeah, so the answer clearly says, for example, there's also the main saddle, the one that Gross and Mendel have, it appears 3 times, which you can roughly see from here. So there's some multiplicity of the saddles.
Can you obtain some useful information about tree-level amplitudes with some massive external states from this information on the cuts that you have?
Depends what some useful information is, I think. But the answer here is always written as a sum of all the polarizations in the middle. So it's not that you can pick out one state and talk about that, because of course that would be very complicated because it has a huge polarization tensor as an external state. Yeah, so in some sense this is an average over many heavy tree-level amplitudes because you're summing over all of them. Yeah, going the other way around is kind of difficult. Like, I mean, if you were actually to construct all these tree-level amplitudes with massive states, it's kind of a mess. Yeah.
More questions? Please, Sarkozy.
Is there a useful way to isolate, say, a loop of massless states and then expand the rest in alpha prime expansion? So suppose we're interested in something like, I don't know, comparing to low energy physics.
Yeah. Yeah, we tried, and I don't know of a useful way, but I would be happy if there is. But,
the massless one, you can essentially get it with a cutoff.
Yeah. Yeah. Yeah, I would be very, in particular, it's very hard for us to like do analytically this alpha prime expansion of the answer and connect to it back. So it will be fantastic if we sort of can take out the massless part, which ironically for us is the hardest, and then do this and then somehow put it back at the end. But yeah, I don't know how.
So if there are no more questions, I have a little question. So if we have a function of one complex variable, we know what is the deformation of contour. It's because we assume that the function is analytic. But what does guarantee, or at least hints on this double analyticity, both in real and complex part?
Yeah, so for this integrand that is of interest here, it's just 2, because it has a very nice Q expansion and so on. But so like most of the, you need to assume for this formula to be true that the integrand, first of all, extends analytically in both tau and tau bar, or tau tilde, as a holomorphic function in the full upper half plane. And so almost all the functions that we have, they have nice Q expansions. So whenever you have some Q expansion of some conformal field theory or something, it converges absolutely, even if you make Q and Q bar independent, right? So for all these functions, it will always be true, but it might be that you can come up with some kind of pathological function that, are you worried about like several complex variables? I mean, there can be funny phenomena happening, but
it's a bit funny that you take real and imaginary part separately and then announce that even in those variables it's analytic.
Yeah, I agree, but in some sense it's an accident that the original modular space was complex. So you could forget about the fact that the modular space was complex, because, I mean, if you have Lorentzian 2D surfaces, of course they won't be complex. They don't,
Okay, thanks. So if there are no more questions, let's thank again Lorenz.
Thanks.